Hi everybody. This is the lecture on section 5.3, which is on double integrals using polar coordinates. So a polar rectangle is a region in the xy plane with 0, or not 0, a less than or equal to r less than or equal to b, and alpha less than or equal to theta less than or equal to beta. So it's in the xy plane, but we're using r and theta, so indicating that we're going with polar coordinates. So it looks something like this. So r equal to a and r equal to b, of course, are circles centered at the origin of the given radius. So that's a0. And then b, over here perhaps, b0. And then angles alpha and beta are represented by lines from the origin, having rotation alpha and rotation beta. So the polar rectangle is exactly this region between the alpha and beta and between the a and b. Okay, that is a polar rectangle. It's not a rectangle in the xy plane, but it's a rectangle in the r theta plane, which we aren't looking at. Okay, anyway. So what we want to do is to show the following. So we will show the following. The double integral over the region R of fx, y, dA is equal to, okay, and instead of iterating with x and y, we're going to be able to iterate with r and theta. So it is the integral from a to b and then alpha to beta f of, well, x is r cosine theta, y is r sine theta, and then the dA becomes r d theta in this case. So the inner integral is with regard to r, and the outer integral is with regard to theta. And then there's this correction factor of r, and you'll see where that comes from in a little while. And by Fubini's theorem, as long as f is continuous, this is equal to, so you can just switch around the dr and d theta. Alpha to beta, a to b, f r cosine theta, r sine theta for x and y, and then r d theta dr. Or you could put the r in here if you want, because r is a constant. That r is a constant. Constant with regard to theta. Okay, so so how do we set up how can we estimate the double integral over r f x y dA for the polar rectangle r? Okay, well, we're going to cut it into subrectangles, just like we did with the ordinary rectangle back in section 5.1. We're going to take the polar rectangle. Let me take the one I have up here. we're going to take this polar rectangle and cut it up into smaller rectangles. So we're going to take R and we're going to split R up into subintervals, however many subintervals we might like. You know, we're going to let it go to infinity, of course. And then the theta is going to be split up into subintervals as well. Like that. Okay, so let's do a different color here. Delta R is equal to B minus A over N, and then delta theta is equal to beta minus alpha over M. Okay, and then the area, what is the area of one of these little polar rectangles? So this little polar rectangle has angle inside here from the origin, delta theta, and then has width right here, delta R. Okay, oh, and by the way, of course, we're going to label the various steps. This is going to be R1, R2, R3, and then B is going to be equal to R4. And then this is less important, but this is theta 1, theta 2, theta 3, and then beta is going to be equal to theta 4, theta m, or whatever it is. So now what is the area of this thing here? Well, the area of a sector of a circle, and then this is going to be the bit of the sector of the circle, say at Ri plus 1, and then the difference between the two is delta R. Alright, so the steps here are delta R, so the difference between the two here is delta R. So what is the area of the small polar rectangles? Okay, well, the area of a sector of a circle, right, so this is the sector of a circle here with angle delta theta here, and the whole radius here equal to, what should we call it? RMS, just call it S, radius S. So the area of the whole sector is, well, what is it? The area of the whole circle is pi s squared. And what is the whole circle? The whole circle is an angle of rotation 2 pi radians. Right? So this is half of 2 pi. So if you're going some fraction of 2 pi, like delta theta, the area of the whole sector is delta theta over 2 s squared. So the area of the small polar rectangle here is, well, it's the area of the outer sector minus the area of the inner sector. So it is delta theta over 2 Ri squared minus, or Ri plus 1 squared, minus delta theta over 2 Ri squared. which is equal to what? So we can factor out the delta theta. So it's 1/2 Ri plus 1 squared minus Ri squared delta theta, which is 1/2 Ri plus 1 minus R, or plus Ri, times Ri plus 1 minus Ri delta theta. Right? Well, what's this right here? That's delta theta. So this whole thing here is approximately equal to, or no, sorry, this is delta R. This whole thing here is approximately equal to, now, so when n is large, Ri and Ri plus 1 are not that much different. So this is approximately equal to 1/2 of 2Ri. 1/2 of 2Ri. Because they're really not that far apart. This is delta R, and this is delta theta. And then the 1/2 and the 2 cancel, and it's just Ri delta R delta theta. Okay, so the area of this sector here, of the red polar rectangle there, is approximately, when n is large, Ri delta R delta theta. So, the double integral over R of f x y dA is equal to, well, it's approximated by the double sum. The sum I equals 1 to n, the sum j equals 1 to m. F, well, x is going to be equal to Ri cosine theta j. Y is going to be equal to Ri sine theta j. And then the area of that little polar rectangle is this. So it's Ri delta R delta theta. Well, it's approximately that. Right, so the double integral is, so instead of using rectangles to estimate, instead of using rectangular boxes to estimate a double integral, we're using these polar rectangles. So you've got this whole area here, and then you've got that polar rectangle right there, and then the height of this box, whose base is a polar rectangle, is given by the sample point for the surface fxy. Right, so instead of estimating by boxes, we're estimating by things that are kind of like boxes. I mean, they're boxes of polar rectangles. So the double integral is approximately, right, the double integral, which is the volume under the surface, between the surface and the xy plane, right, and we're estimating that volume between the surface and the xy plane, okay, by using these funny polar rectangle boxes, right, and the volumes of those boxes is the sum of the height times the area of the base, which is approximately this. Ri delta R delta theta. And so if we take the limit as m and n goes to infinity, then the volume is precisely that. Right? Thus, double integral over R f x y dA is equal to the limit of the Riemann sum. And the limit of the Riemann sum is exactly what we've been saying here. It's the iterated integral from a to b and alpha to beta, f r cosine theta, r sine theta, r dr d theta. Right, which is the result that we wanted. Okay? So let's take an example. So let's find the volume above the xy plane and, well, the volume of the solid above the xy plane and inside the paraboloid z equal to 1 minus x squared minus y squared. Right, so a picture of this would be as follows. So 1 minus x squared minus y squared, that's the paraboloid, that we've been looking at quite often, but it's upside down in this case. It's facing down. Right, so here's that paraboloid. And we're looking for the volume captured underneath that. So z is equal to 1 minus x squared minus y squared. So the volume is the double integral over r of 1 minus x squared minus y squared dA, where r is the projection of the surface straight up or straight down onto the xy plane. If you imagine a light source coming from straight up top, right, with light rays pointing straight down, when it hits this surface here, okay, where is the shadow? Well, the shadow is going to be this circle down here, right? That's the region R that we're going to need to integrate the function 1 minus x squared minus y squared over. Okay, so this region satisfies is the one inside the curve 1 minus x squared minus y squared equals z. Which z? Z equal to 0. It's the level curve with the xy plane. Right, which is equal to, so 1 is equal to x squared plus y squared, which is the unit circle. Right, that's the circle of radius 1. So that's R. How can we express R as a polar rectangle? What is the bounds on the radius? What is the bounds on the angle? Well, it's quite simply the whole circle of radius 1, the whole disk of radius 1. So radius is going from 0 to 1, and angle is going from 0 to 2 pi. So we describe the disk as a polar rectangle with a full rotation of 360 degrees and a full range of radii from 0 to 1. Right? So, okay, the volume is this double integral. The double integral over r, 1 minus x squared minus y squared. So double integral over r, 1 minus, I'm going to write it like this, x squared plus y squared dA. And now we're going to convert to polar coordinates. Okay, so double integral 0 to 1 for r, 0 to 2 pi for theta. All right, this is the r. 1 minus, and what is x squared plus y squared? X squared plus y squared is just r squared. And then dA becomes r dr d theta. Okay? So, let's clean up that expression. So it's r minus r to the third, dr d theta. Antiderivative with regard to r, 1 half r squared minus 1/4 r to the fourth, r equals 0 to r equals 1. Right, so evaluating from 1 to 0, you just get 1/4. Just get 1 half minus 1/4. The whole thing is 1/4. And then the integral from 0 to 2 pi of a constant, right, is just that constant times the length of that interval, 2 pi minus 0. Right, the integral of k from a to b dx is just equal to k times b minus a. Let me write that over here. So the integral from a to b of k dx is just k times b minus a. Right, so over here we just get 1/4 of 2 pi minus 0, which is pi over 2. So that is the volume underneath that upside down paraboloid there, just pi over 2 units cubed. Let's try another one. Oh, what happens if we didn't convert to polar coordinates? What would happen in that case? So what would happen if we tried to do this integral in rectangular coordinates? Okay, so it was the double integral over r, 1 minus x squared plus y squared dA, where r is the unit circle. Right, and instead of calculating over the entire unit circle, you'll notice that, that surface is nice and symmetric around the xy plane and the xz plane. So let's just calculate the volume of this bit and multiply the answer by 4. So let's just calculate 1/4 the volume to simplify matters. Okay, so the double integral over r of 1 minus x squared plus y squared dA is equal to 4 times the double integral, right, over 1/4 of r, 1 minus x squared plus y squared dA. All right, and what is that 1/4 of r? Well, it's this quarter circle of radius 1, quarter of the disk of radius 1. So that's 1, and this is that disk. So how do we describe this region in terms of x and y? Right, remember, this is the circle of radius 1, which has got equation x squared plus y squared equal to 1. So you can rewrite it as y is equal to the positive square root of 1 minus x squared. So this is 0 less than or equal to x less than or equal to 1, and then the y is between 0 and that quarter circle. So it's 0 less than or equal to y less than or equal to 1 minus x squared. Right? So this is equal to 4 times the iterated integral. So y goes from 0 to square root 1 minus x squared, and then x goes from 0 to 1, 1 minus x squared minus y squared. We'll just write it as 1 minus x squared minus y squared. dy dx. Okay. Antiderivative with regard to y is equal to the integral from 0 to 1, 1 minus x squared times y, minus 1/3 y to the third from y equals 0 to y equals square root 1 minus x squared dx. So this is equal to the integral from 0 to 1, 1 minus x squared times y, which is the square root of 1 minus x squared, minus 1/3 square root 1 minus x squared to the third dx. So this is equal to the integral for, or I lost my 4, didn't I? 4, 4, 4. Integral from 0 to 1. Well, this becomes 1 minus x squared to the 3 halves. All right, we got 1 minus x squared to the 1, 1 minus x squared to the 1 half. Added together, give me 1 minus x squared to the 3 halves. Same thing here. Minus 1/3, 1 minus x squared to the 3 halves. So that's 2/3. So 8/3, integral from 0 to 1, 1 minus x squared to the 3 halves dx. How do you solve that integration? Well, how do you get that antiderivative? Does anyone know how that works? Do you remember? That needs a trigonometric substitution, right? So I mean, already we've really, we really see the advantage of this approach, given, certain types of regions and certain types of functions. I mean, calculating this integral, which was pi over 2, that just took a few steps here when doing it in polar coordinates. Now that we switched to rectangular coordinates, we've boiled it down to this, which needs a trigonometric substitution. I mean, which is, takes a little bit of doing. Let's do it. So let x equal sine of theta. So a different theta. What should we use instead of theta? Sine of gamma. So let x equal sine of gamma. So dx equals cosine of gamma d gamma. So this is equal to 8/3 integral from x equals 0 to x equals 1, 1 minus sine squared gamma, cosine gamma, to the 3 halves, cosine gamma d gamma. Alright, well, when x is equal to 0, this is sine of 0, so gamma is 0. When x is equal to 1, this is sine of pi over 2. So it's the integral for gamma equals 0 to gamma equals 1. And then 1 minus sine squared is cosine squared gamma to the 3/2 cosine gamma d gamma. Since we're in the first quadrant, 0 to pi over 2, since we're in the first quadrant from 0 to pi over 2, cosine is positive. So the square root of cosine squared is just cosine because it's already positive. You don't need to, you don't need to do this sort of thing. Right, because cosine might be negative. No, you don't need that here because cosine is positive already. So no absolute values are needed. So this is cosine to the third. So we got a third from gamma equals 0 to gamma equals pi over 2. Cosine to the fourth, gamma d gamma. Crazy. Cosine to the fourth. So let's find the antiderivative. I mean, if you remember how that goes, you need to use the double angle formula twice. So this needs double angle formula. Twice. The double angle formula was that cosine squared x is 1/2 1 plus cosine 2x. So that gets rid of the cosine squared for you, but then you got to square it again because it's cosine to the fourth, and then you get down to cosine 4x. But let's just take a shortcut here. So antiderivative cosine to the fourth x. Right there. So it's 1 over 32, 12x, and then we got sine 2x, sine 4x. So let's use Wolfram alpha instead. One over 32, 12x. Or 12 gamma in this case. I lost my 8 over 32. 8 sine 2 gamma. And then sine 4 gamma. So I lost my 8/3 there. Evaluated from gamma equals 0 to gamma equals pi over 2. Alright, so this becomes 4, so it's 1/12. So 12 gamma from pi over 2 to 0 just is 12 pi over 2. And then this is 0, right? Because sine of pi is 0, and sine of 2 pi is 0, and sine of 0 is 0. So these are just 0. All right, plus 0 plus 0, and in the end, what do you get here? Pi over 2. Right, same answer as before. Okay, same answer as before, but much more work. Was involved. What's the essential advantage that happened? Why was this so tricky? I mean, look at that. I mean, I didn't even do this part, right? And that part's another half a page right there. I just looked it up, the antiderivative on Wolfram alpha. And then look at the whole calculation in polar coordinates. Why? Why was it so different? What's going on? Essentially, this integral in terms of polar coordinates, it knows what the area of a circle is. It knows what the area of a circle is, right? I mean, we use that notion, right? The area of the sector of a circle is half the angle times the radius squared, right? So that's built into it. How do we know that the area of a circle of radius s is pi s squared? You know it by a trig substitution. The first proof you would have seen of this area formula, okay, used the trig substitution from Calc 2. Okay, so it was necessary to use trig substitution to actually prove that, I mean, there are other ways to do it, but this is the most straightforward one, to actually prove that the area of a circle is pi times r squared. It's 4 times the integral from 0 to pi over 2 square root r squared minus x squared dx. That's the area of the circle of radius r squared, and that requires the trig substitution x equals r sine theta. So you do that trig substitution once, and then you know the area of a circle, and then that's built into this polar coordinate calculation. So it sort of got over that whole technicality of what the area of a circle is. Rectangular coordinates don't have the area of a circle built into it. Okay, you actually have to calculate it, which you should have done in Calc 2. If you're in my Calc 2 class, you would have done it. But I mean, there's definitely some work to be saved in doing it that way. All right. What about some more general shaped regions in polar coordinates instead of just polar rectangles? So more general regions in polar coordinates. If you've got r equals f of theta like this, and then r equals g of theta like that. So let's put r equals f of theta, or I switched them, didn't I? R equals g of theta. Well, let's make this one f. R equals g of theta. And then we'll have some angle alpha and beta. Theta equal to alpha, theta equal to beta. Then this region in here, right, has got a bit more general shape than just a rectangle. So this region R is alpha less than or equal to theta less than or equal to beta. And then g of alpha, or g of theta, is less than or equal to r is less than or equal to f of theta. Okay, so angle has to come first, just like with more general regions in rectangular coordinates. The first variable is bounded by constants, the theta, and then the r is bounded by functions of the first variable. So you can't just flip them around. This one, you have to have r first and theta second in order of integration. So now, if you have some function f, x, y, d, a over r, this region r here, you can calculate it in terms of polar coordinates as the iterated integral from g theta to f theta, and then from alpha to beta, f r cosine theta, r sine theta for x and y, and then it's r d theta. So it has to be dr d theta. You can't flip those guys around. With the basic polar rectangle, you can, because they're both constants. Okay. So for example, find the area of one leaf of the three-leaf rows, r equals sine 3 theta. Find the area of one leaf of that 3-leaf rows. So the 3-leaf rows was this. See if I can get a good one. Or no, sorry. There it is. Sort of. Alright. Should be nice and symmetric. So this is a radius of 1. I know this one is sticking out more, but my hand is shaking today. So that's r equals sine 3 theta. So one leaf of that rose is right here. And when is that leaf happening? So it happens when r goes from 0 up to this max here, back down to 0. So where does r, for what values of theta does r go from 0 to 1 to 0 just one time? So 0 equals sine 3 theta, right? So where's the first couple angles where sine goes from 0 positive back to 0? Okay, well, the first angles, well, let's write down a few angles. So 3 theta is equal to 0 degrees, right? And then 0 radians, pi radians, 2 pi radians, 3 pi radians, right? Every multiple of pi, integer multiple of pi. So theta is 0, pi over 3, to 2 pi over 3, to pi, etc., etc., etc. Right? So one leaf of the rose happens from 0 to pi over 3, 60 degrees. So this is theta equal to 0, theta equal to pi over 3, and therefore right in the middle there is theta equal to pi over 6, where it reaches its maximum. Okay, so the petal of the rose P is, as a general polar region, 0 less than or equal to theta less than or equal to pi over 3. And then we're just going for the radius from 0 out to sine 3 theta. 0 less than or equal to r less than or equal to sine 3 theta. Right? That is the inside of the rose, right? Here's the various r measurements as you go through different angles. So we're going from 0 out to the outside of the rose, to the curve of the rose. So that's the boundaries for r. Okay. So how do you measure the area of a region in the xy plane? All right, so the area of the petal is the double integral of the petal of just 1 dA. That gives you the area in general, right? For any region in the xy plane, if you just want the area, just the double integral of 1. Okay, so let's convert to polar coordinates. So it's the double integral from 0 to sine 3 theta, and then 0 to pi over 3, 1 dA. And dA becomes r dr d theta, right? Leaving out the 1 there. So antiderivative in terms of r, 1/2 r squared. 1/2 r squared from r equals 0 to r equals sine 3 theta d theta. So this is equal to the integral from 0 to pi over 3, 1/2 sine squared 3 theta minus 0 d theta. Double angle formula. Sine squared x is 1/2 1 minus cosine 2x. Right, double angle formula. So this becomes 1/4, half times a half, 0 to pi over 3, 1 minus cosine 6 theta d theta. Antiderivative, this is just theta. Antiderivative cosine 6 theta, 1/6 sine 6 theta, all evaluated from theta equals 0 to theta equals pi over 3. Right, well, sine, so 6 times pi over 3 is 2 pi. So sine of 2 pi is 0, and sine of 0 is 0. So this bit is just 0. So it's 1/4, and then the theta goes from 0 to pi over 3. So it's just pi over 3 minus 0, minus, and this whole bit here is 0. So you get pi over 12 is the area of one leaf of that 3-leaf rose. Okay? Okay, so that's the end of the lecture on this section.